The rate of growth of a population of fish is given by, and so this is a differential equation again. Basically, anytime you're given an equation of the derivative, we're learning a new word for this. We're calling this a differential equation. If the initial population was 200 fish, how many fish were there at 4 years? So what a differential equation is modeling is you have been collecting data from some sort of real life situation, and you've come up with a formula for how fast things are growing. Then you look back and say, we had some data that the population of fish started with 200. Can we take this rate of growth and translate it into a new equation that can figure out the population of fish at any time? And then most likely in a real life situation, then you would test your model to see, is it accurate or not? And if it's very accurate, then you're like, hey, this is really helpful. So what we're going to do is we're going to say our population is going to be the integral, the indefinite integral of this. We do our rules where we add 1 to the exponent and divide. We can simplify this. An initial, this is important because if we don't know that initial means time is 0, we run into a lot of problems. So anytime something is saying an initial population, an initial velocity, an initial displacement, you know that that's happening at time is 0. So we can plug in 0 for t, 200 for the population and solve. And then once we've got our c value, now we can find the population at any time. And we plug it in for 4 years and find out there's 1,000 fish. This is, in a sense, a differential equation because we're starting with velocity. You know that this way is the derivative from displacement to velocity to acceleration, and now we can work backwards on any of them by doing the indefinite integral. So if you know the velocity and want to find the acceleration, you are going in this direction, we will take the derivative. Minus 8 meters per second squared. I'm trying to think of a situation that would reduce gravity by a little bit. What would you have to be?
Higher up in the sky.
High up in the sky enough? Okay.
Shut up, Mark.
I was thinking more fun like jumping into a big bubble bath of just foam, having enough foam that it's slowing you down a little bit.
Is that
It's not gonna, well, like you would slow down if you jumped in water, right? So what kind of density would you need of a substance in between so that your ability to fall down would slow down, right? It's got to be something.
I feel like you put a lot of bubbles.
You would need that. The bubbles is probably not enough. I think you would. Yeah, if you think this'll, you'd be like, I'm gonna jump off a building, but first I'm gonna fill it full of bubble bath and I'll be safe. That's probably not a good idea.
Water bucket.
Initial displacement is 5 meters, so now we can find an expression for S in terms of T. So now we integrate, and I usually find these velocity questions quite straightforward as far as the numbers, easy to integrate, add 1 to the exponent and divide, plug in 0 because it's initial, find out the value of C. That is not a -5, that is just a challenge to equal sign. So some of you have taken physics and you've developed a lot of formulas that you're able to use, and that's great. One of the things that we can do in calculus is say, instead of using all of those formulas, can we just use the idea of calculus to figure out some ideas? And that's sort of what happens in this next question. A ball is thrown upward with initial velocity of 64 feet per second from an initial height of 80 feet. How long will it take the ball to hit the ground? Okay, and now if you had physics formulas, then you apply those physics formulas and you solve your question, right? But then someone's like, I didn't take physics. Could I use my calculus without the use of those formulas to figure this out? Okay. We're going to use feet per second. That is negative 9.8 meters per second converted to feet per second. I don't know if you've ever used the negative 32. So there are some things that we do have to use what we know gravity is. The other option would be to change everything to meters and then deal with it and convert your units back at the end. Interestingly, is if you would go back to your grade 11 textbooks, you will see negative 16 happen a lot of times in parabolas because they're using feet per second. And they also use negative 5. Half of 9.8 in grade 11 is 5 because it makes the math a lot easier to teach. So we see those kind of things happening in other courses. So if you know your acceleration, you can work backwards from acceleration with the integral. You know that your velocity will be negative 32t, and this, I'll put a plus c1, because eventually I'm going to go to a displacement formula as well, so there would be a plus c2 there. And since you know an initial velocity, we can solve for c1. So now we have a velocity formula, just based on calculus. Integrating again gives us our displacement, or our height formula in this case. Here's the half of 32, you get minus 16. So in grade 11, anytime you throw an object up into the air, it made a parabola. Everybody was happy. And those parabola equations, if they were done correctly, often had either a minus 16 if they were dealing in feet, or they used a minus 4.9 if it was a calculator question and they used meters, or they used a minus 5 if it was not calculator and they wanted to be close enough. I know my initial height, so I can plug in 0 for time, and I find out that C2 is going to be 80. So now I have a height formula. How do I solve when it hits the ground? I just need to put in 0 for my height. And solve for t. Now it's a parabola that's going down. And for this one, I would say we could use our graphing calculator to find out what this value is. This parabola that's going down will look like this with an initial height of 80. So something that I have in this formula, any parabola, your initial height, I have there is S0 as an initial height. That's at 80. Our initial velocity always shows up here. And what's in front of the t squared is always half of gravity. So if we plug this into our calculator, we're going to get two x-intercepts. We're going to get one here and one here. Obviously, the negative one is not true. Right? In a context question, when we're solving, we're going to be looking for this one, because you can't throw a ball up in the air and say, yeah, it hit the ground 8 seconds before I threw it. That doesn't make sense. All right, I'm going to end this video here.